Okay then, we're already like 10 minutes late, so I will just start. I think a couple of people arrived right now. So quickly to introduce myself again. I was here yesterday. I think there's no new faces. I'm Mark. I'm a PhD candidate, Graduate School of Informatics. Will become D3 in next week, I guess. So I will do this lecture. Actually, I don't know if you catch it yesterday. We switched around the lectures quite a bit. Well, quite a bit. So the first one is Python. Right now, I do it. And then after lunch break, there's OpenCV. And then in the end, in the afternoon, there's Unity. So I will do Python, David will do OpenCV, and then I will do Unity again. But I think we do the whole day in Linux. Everything will be Linux-based, Unity and Python. Actually, OpenCV is also based on Python, so we will just continue Python there. Python all day, woohoo. Yes, I think you already downloaded these materials. So I will first give a quick introduction to Python and talk about why it would probably be a good idea to learn Python. So Python has been kind of exploding in recent years. It's one of the most used programming languages, especially in the last couple of years. It even surpassed Java, which was very big in the not 90s, but like zeros. So yes, it got pretty big, which is mostly related to machine learning. So at the university, especially if you do lots of prototyping, if you do lots of stuff with machine learning, if you do like, let's say, deep learning, then you will probably use Python because almost every deep learning-based library is based on Python. So yeah, it's, I mean, the leading students will most definitely use Python at some point, but I think the DI students will also probably come in touch with it if they ever use any machine learning or so. So yeah, at the moment, like 50% share, I think that's like out of data mining, data science companies. There's also some statistics. They're like already 2 years old, but if you look something like this, just since 2014 to 2017, within 3 years, Python got from like 20% usage to like 50% usage. And if you get statistics from 2019, like right now, it will probably be like somewhere here. Like it's at the moment it's like 80-90% because literally everybody uses Python for everything. So yes, it's pretty important. So what is Python? It's a general purpose programming language. It's open source, like Linux. And it has a very large and comprehensive standard library. So that's one of the reasons people usually use it. Not only the standard library, but there's also like 1 million packages. So you can basically download anything from like machine learning stuff, plotting, all kinds of like data science, like processing data. You can do like language processing, all kinds of stuff. Everything comes in packages, so it's very handy to just install packages and use it. By design, it has a very high readability of code and very quick prototyping. So especially the DII people, I think some of you used something like C before, or maybe C++. That's always a bit, if you do big projects, it's like lots of setup. You need like make files. You need maybe like some header files if you have multiple files. If you use Python, it's very quick. It's one file. You can even write like graphic interfaces within like a couple of lines. Later, in the end of the lecture, we have like machine learning. And it's basically like this kind of snippet, like maybe 10, 15 lines, and you do a full machine learning of some kind of data set. So you can very quickly come to results. That's meant by quick prototyping. And it has automatic memory management, which is also nice if you come from C. So there's no mallocs, there's no free, everything is done automatically. One unfortunate thing with Python is basically that there's different versions, mainly Python 2 and Python 3, and they are not really that much compatible to each other. So lots of Python 2 code is not compatible with Python 3, and the other way around. So always keep that in mind. Python 3 is obviously the newer one. We will use it here, but just if you come in contact with Python 2 code, it might not work, or you get into trouble. But then again, Python 3 is the future, so almost all libraries work with Python 3. Just some small example. If you like you had Java yesterday afternoon, I think. Most of you like touched something like this, which is C, C++, C#, Java, name it. Basically looks like this. Some if statement like if x is equal to 10, you set y to 0, something like that. You probably know it like that. Python uses a bit different syntax, like there's not these curly thingies. Python uses a completely white-spaced layout. So basically, whereas here, basically, this space has no meaning. The brackets are important. But in Python, actually the space has meaning. So if you forget this, it doesn't work. Like the indentation is important, stuff like that. It's a bit different. It looks different than other languages, but as I said, it's a very often used language. So just bear with it. Some ways to run Python. It's a scripting language, very similar to like MATLAB, which we did yesterday. After lunch, I think. So basically, it has like this kind of terminal where you can just put in commands and just calculate stuff. There's no compiler like Java. You can do stuff interactively, but you can also make like scripts where you just run multiple things in a row. I think you basically did the same thing in MATLAB yesterday, so you should be somewhat comfortable with the idea. So you can do stuff like that. You can like A is 10, B is 20, and then A plus B, and the result is 30. Something like that. We will go in that. We will go into detail on that later. You can also run scripts. So you just put the same stuff like A equal 10, B equal 20, and then print A plus B. And you can just run it on the terminal as a script file, and the result is 30. Something like that could also be. So you can make long scripts with all kinds of machine learning stuff, and then you run it. Also very similar to MATLAB, I guess. So there are some other tools. One very famous, I guess, is called Jupyter, where you basically you have like a kind of like interactive interface to Python in your browser. It looks like this. We don't go into detail on that, just so you know about it if you ever want to use something like that. It's nice because, like, if, for example, in your lab, if you have like a very juicy GPU server or something like that, you can like connect to the server and just run everything through the browser and run your files inside that kind of interface. So that's also very often used. There's lots of other stuff. There's editors, there's IDEs. Android Studio, maybe you used yesterday in Java, I think, maybe. Like this big application where you program in. There's stuff like that for Python too, but you can just use any editor. So going back to the packages, which I talked about in the beginning, basically, I don't know if the number is current, maybe it is, but it's probably bigger right now. I think the number is from like last year, but there's over 130,000 extra packages. So you can just go to the terminal, install extra stuff. Like here, all kinds of different, I think on the next slide I have some kind of examples, but basically you can do whatever you want, like machine learning, text processing, image processing, deep learning, name it. There's probably a package for it in Python. So Python has a built-in way to install new packages. You can go crazy and just install stuff. There's also a thing called Anaconda, which is basically like just install Python plus all kinds of packages in one big download, and you just install it into one directory. It's available for like Linux, Mac, Windows. You can just download it, install it on your computer, and use Python. Anaconda is very commonly used in academia because it has all packages you basically need for your research. So when you look into packages, there's like SciPy, NumPy. I think these two we talk in this lecture today. So SciPy would be stuff like not like analysis, all kinds of mathematics stuff. NumPy is most of the algebra stuff and linear algebra. There's stuff for numerical computing like Theano. Theano also does deep learning stuff, I think. There's machine learning. This one is very often used. It has stuff like support vector machines and random forests and all kinds of different algorithms for machine learning. There's lots of different deep learning libraries. This list is very short, but there's probably like 10 times that. There's image processing, OpenCV. This one, Daryl will talk about that in the afternoon, after lunch. And then there's other stuff like Pandas is very big for data analysis, like you can pre-process data with that, etc., etc. So I very briefly want to talk about Anaconda. That's like a one-click download solution for Python. It's already installed on all these computers, so you don't need to do anything right now. It's already on there. But if you ever want to use it on your own laptops or in the lab or at home, I don't know, this is probably the go-to solution. So it's like it installs Python, R, Scala. It's basically a big download which has all kinds of data science stuff. And yeah, it's one-click installer, Windows, Mac, Linux. Very handy. Do you have the link? Okay. So yeah, you go to anaconda.com, just click it as a download. It's available for Python 2, Python 3. Handy. There's also like a repository where you can install extra packages. So for example, OpenCV is a lecture from David. If you want a package for that, it's available in the repository and you can just install it. Again, on these computers it's already done, but if you ever need that. And then lastly, before we look into the actual language, I quickly want to talk about documentation, because obviously I won't talk about everything in Python today. But if you want to use it, if you need some help, if you don't understand anything, there's a very, very, very good documentation on the website of Python. So here's an excerpt in Japanese. It's also available in English, or a couple of you are in Chinese. Like it's also Chinese available, or Korean, etc. Any language. I can quickly basically you just, if you Google something like Python docs, here's the one in Japanese because we're in Japan, but down here is in English. You can also get it in other languages. But what it is, that one is slow right now. Let's use English. So there's tutorials, there's library what's that? There's library references, all kinds of stuff to get you started. There's also where is it actually? You can basically Google any commands. So like, let's say, I don't know, away. So let's search for array. And then there's like different pages related to array. So if you have used like the Python for array, the module in Python for array, you can get like all kinds of documentation, like what functions does it have, etc., etc. So whenever you need any help, this is your go-to. Or Google. So going back to the lecture. Yeah. One thing in Python is basically whatever you use, the chances are that it is very good documented. So also the libraries, all the modules, you have very great documentation. sklearn, also scikit-learn is like the machine learning one. So that's very helpful. Like I can actually also very quickly go to that one. Scikit-learn docs. Could be faster. So that's the machine learning one. You have like all kinds of quick start guide, user guide, etc. tutorials. But yeah, I mean, you get the idea. Basically, there's also documentation for like the algorithm itself. So even there's some guide on like how to use SVMs, how to use like nearest neighbor, etc., etc. It explains some kind of like the background stuff behind it. So it's actually, even if you don't use the library, it's actually a good lookup for all kinds of like how does classification work and what algorithms are there for classification, stuff like that, including examples. It's available. So very, very helpful. Even if you don't really intend to use the library, you can just use it to look up the math behind it actually, or at least get some idea on it. So yeah, same for NumPy, etc. These two, especially, we will cover these two, like sklearn and NumPy, as part of this lecture. So if you ever need help on that, these links might also help you. So yes, next I would like to take a quick look into Python itself. So basically, what you can do on these computers, I think, you can basically like go to the terminal. Why is it so crazy slow? Nice, it used like 400% CPU again. Why does it use 400%? So you can start Python using the command Python. And it should look somewhat like this. Maybe the versions are a bit different depending like which computer you're using, but it mostly looks like this. So inside here, you can just use Python. You can start with like simple stuff like I should switch the keyword. So let's use that one. A equals 10. B equals 20. A plus B. So that was very high-level math. You can do stuff like this. You can do stuff like for loops. So I think David did something very similar yesterday in the Bash scripting unit. So you can do stuff like this. For I in range, print I. So that command would go like I equals 0, I equals 1, 2, 3, 4, 5, etc. until 10, and just print everything. So you can do it like this. And then for every I, it's printed. It's very similar to the one you did yesterday with David, where you were supposed to like print one number every 1 second or something like that. You can do something like that in Python too. Note, like for example, this one, it's range 10. It starts with 0 and ends with 9. So it's like off by 1. So it's still 10 outputs, but it's like it starts with 0. In Python, everything starts with 0. Probably should get used to that. So there's also like different syntax for that. Like you can just put like start and end. For example, if you want to do it like if you want 10 outputs, oh. So you could do something like this if you really want this from 1 to 10 idea, then you start at 1 and go to 11, so that it ends like with the 11th argument, so the last output is 10. It's kind of weird, but yeah, you get the idea, I think. So you can do all kinds of stuff like this. You can also nest them. So for example, for I in range 3, for y in range 3, and then print out I and y. And then you basically get both of them, which is kind of handy if you want to do stuff like matrices. So then that would be like the x and y, like, yeah. If you have like a 2D matrices, you can do it like this, y. You could also make like 3D if you nest it 3 times. Stuff like that. And stuff like this runs from the inner loop to the outer loop. So first y gets increased, then I gets increased, and y again, and then I gets another increase, and y again. So something like that. Again, it starts at 0 and goes until 2 for the range 3. So keep stuff like that in mind. There you can not only like iterate, like the last examples were like, okay, let's go over numbers. So like I is a number, like 1, like 0, 1, and 2, and it goes up. You don't need to use numbers. In Python, actually, you can use anything. Like you can, for example, this is an array of colors. So you have like, we define like colors to be equal, like it can be red, it can be green, it can be blue, etc., etc. So that's an array of elements, and then we can just iterate over them. So we can for every element in colors, and then it prints out red, it prints out green, blue, etc. So let's quickly do that. Colors. It's very fast today, my laptop. Oh. Colors. What else could we use? Objects. And then pencil and laptop and bottle. And then for an object in objects, print the object. And now basically it just prints these one after another. It can be very helpful if you have some kind of data. The data often comes as a big array, like maybe not 3 entries, but like 1,000. And then you can, for every object in your data or for every entry in your data, do something. Print is obviously very easy, but you can also like do some math in it, like for every object, do some math, stuff like that. Let's skip the bottom example. So next we do something very similar to what Suzuki-sensei did yesterday in MATLAB. There's a package called NumPy, which basically does all kind of some scientific computing. So NumPy is mostly linear algebra, I think. It also has some kind of numerical math and stuff like that. But so that's a very handy package if you use any kind of data science with math. So that should be very similar to Suzuki-sensei's lecture yesterday for MATLAB. NumPy is already installed on these laptops, so you can basically run it like that. So you can do like import NumPy as NP. That one kind of makes you be able to use NumPy as NP. So whenever you type something like this, NP dot, you get a NumPy function. And one would be array. So this is the way you would do something like this array, I think, would be defined like this. So yeah, it's written here. So you can like define this kind of array, like this, first line, second line, and then just putting A basically just gives it as an output, so you can look what's the contents of A. That's the contents, we just define it. And then you can do stuff with it, like you can do math, you can do different like multiplications of matrices, etc., etc. We do that on the next slide. But first, for example, you can do something like a V-shape. So a V-shape would change like, this is 3 times 2, like 3 per row and 2 rows. But you can do a V-shape and then it changes the change from two elements per row and 3 rows. And you can also access single elements, so you can change. Like for example, here there's we do a V-shape, so now the array would be something like this: 0, 1, 2, 3, 4, 5, 3 rows. And you can say, okay, you want to change one element. So this one is element 1, 0, which would be like, well, as I said before, in Python everything is like off by 1. So basically the element 1 is the second row, and the element 0 is the first element of the second row. So you could change that to 6. And from 0, 1, 2, 3, 4, 5, now it becomes 0, 1, 6, 3, 4, 5. So you can change single elements using something like that. There's some kind of other stuff like arange. Arange is just a quick command to do something like this. Like on the last slide, this one is like you type it, like you want to 1, 2, 3. 0, 1, 2, 3, 4, 5, etc., etc. But if you want to make a very big matrix, like 1,000 elements, you probably don't want to name all of the elements. So there's a couple of extra functions, like this arange function, for example. You can just make like from 0 to 1,000, and then you make a big matrix, 1, 2, 3, 4, 5, 6, 7, etc., until 1,000, a big. You can use something like that command. There's also like a command zeros, where you can just make a big matrix full of zeros. There's one command for ones, where you make a big matrix of ones. You get the point. There's a couple of other functions, hstack, vstack. It basically like moves around the matrix, like the elements inside. And then there's a couple of nifty tricks with data access, which is kind of Python-ish, like it's mostly used in Python, something like that. So for example, if you define a big array like this, D would be this big array, so it's like 3 times 4, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that would be an example matrix. And now, for example, we only want the first line and the third line. Python has this weird syntax where you can select single lines and just make a new array out of them. So it grabs out these 2 lines and makes a new element just out of these 2. Maybe 2 at once is a big, a lot, but I mean, if you're used to Python, if you're used to C, you probably know something like this. So actually, I should import NumPy as NP. And then, like we have an D is an array. I'll just make it one-dimensional, so we have 1, 2, 3. And in C, you know, like this. So this gets the third element, which is a 3. So you can just access stuff like that. The same would, by the way, also work for the objects one we defined up here. So if you want laptop, that's the second element, so 1. And you just get the one laptop. if you have like a, let's say like this, if you have like a, now D is bigger, and now you can also access it like this. So you want like the, this one is like the second line and the third element, so that's the 6. But there's also like this weird syntax, I think. So this is syntax you probably won't get during this lecture very quickly because it's very unintuitive, I think. But you can just look it up afterwards, or like whenever you need it, just Stack Overflow it or Google it. You can get like a full line, for example, using this colon syntax. Like I think what it basically does is like it takes like the 0th line, which is that one, and all elements of that line, which this colon says. You could actually also continue and like you only want the last 2 elements. No, that's now the middle element. Like you can play around with this and like change what part you want to grab out of the original one. You can also do, I think, the opposite. No, that's all now. What do I actually want to do? I'm not sure. I mean, it's mostly try and error, even for me. So yeah, I think that one I was actually supposed to do. So basically, yeah, the one in the top, basically, it just gets like these 2 lines, grabs out of it. This one actually, if you like kind of reverse it, like the column goes in the front, you can like just get the columns. So this gets this column, and remove the middle column. Stuff like that. It's very handy if you, especially if you deal with big matrices. Like if you have like 1,000 times 1,000, and you only want maybe the top left part, you could just grab it out of the full one very easily. There is array calculation. Well, that's just output. A plus B. You can. It's mostly the same Suzuki Sensei did for MATLAB yesterday, I think. Plus minus, there's multiplication of these 2 would yield to that one. And there's also division, all kinds of other stuff too. There's also, I think, there's a function for dot product, for dot multiplication. So MATLAB yesterday, what Suzuki Sensei did is basically a software dedicated to matrix math. Python doesn't really have like such sophisticated operators like a dot product, but there's still a function for that. So you can, like there's NumPy, like np dot, and then you can use it to do a dot product. Ah, yeah, we have an example of that actually. So here we again have A and B, 2 different matrices, and now we define C, which is like the what's the English word for that? T? Traverse? No, what's the T in English? Transpose. Yes, thank you. So that's a transpose element, like just 45 degrees, 90 degrees. So you have that, which is just b dot t, and then there's also a dot function. So like so that array dot multiplication with c with that one would result in this one. So yeah, matrix multiplication. NumPy is very big for that. Any confusions? Any questions? Any suggestions? Everybody fine?
You just mentioned zero indexing.
Yeah, I did that. But I mean, I can do it again, which is probably a good idea because it's very hard to like people miss it all the time. Like here, for example, very different to MATLAB. Again, I said before, there's like this thing called zero indexing, where basically when you access elements, it's always counts from zero. So this one would be the second element, so this row, and then the zeros element, so that's the first element in that row. So be careful with that. Whenever you want to access something or whenever you want to change something, everything is like, if you think of the second row and first element, it's 1, 0. It's not 2, 1. Yes. Yeah, so much about NumPy. There's not, I maybe quickly want to go into that documentation too, if my laptop wouldn't be so crazy slow. So there's also NumPy. So numpy.org, fundamental package for science computing. Yeah, so basically it's like the main library for Python for anything related to mostly matrices, but also some other stuff. What makes NumPy very nice to use, and what's basically what's the reason a lot of packages also use NumPy, is that NumPy for once is written in C, so it's very fast. Even though Python is script-based, so Python is actually a bit slow sometimes. But whenever you use NumPy, it falls back to C, so the backend is written in C, and it's actually pretty fast. The other thing is that NumPy, I mean, we just talked about it, but it just comes with lots of matrix stuff, which is also obviously often used for lots of computer science stuff. So whenever you have stuff like machine learning, whenever you have stuff like image processing, you often need matrices and big arrays, multidimensional arrays. So almost every other scientific library in Python falls back to use NumPy, so it always comes in a package. Like OpenCV, what David will present after lunch, it uses NumPy in the back end for stuff like, basically when you load an image, I think in MATLAB, an image is also a big matrix, so you have like, for every pixel you have some kind of numbers. The same is true for OpenCV and NumPy, so it's a big array which is loaded as NumPy. Now getting is probably the wrong one. Tutorial sounds good. There's actually even a link NumPy for MATLAB users, so if you're more familiar with MATLAB, go crazy on that link. But, so yeah, the much more detailed introduction to NumPy would be over here. The range stuff and the reshaping we just had, I think it's mostly the same examples as in the lecture. You can go further from that. Like basically, most stuff in linear algebra you can do it somehow with NumPy, and it's fast, as I said. Going from that, I would like to go into the second part of the lecture. Now we switch from NumPy to a different library, which is called sklearn. So sklearn is basically everything related to machine learning. So you have SVM, support vector machines. You have random forests. You have nearest neighbor. You have all kinds of different algorithms, you know, from machine learning. So I think you already downloaded my link from the beginning of the lecture. This is a different link, but it has the same content, I think. So I think basically what you downloaded, there should be like some folder called Python source code, and then there's another folder called Py, and there's a couple of scripts inside there. We can use it, or you can use it to play around with. I will go over these scripts now. Basically, there's a couple of examples using scikit-learn for machine learning. So as I said, it has all kinds of different stuff already implemented. There's classification, regression, clustering algorithms. There's also dimensionality reduction, which is basically stuff like PCA, and other stuff for model selection like grid search, cross-validation stuff. It has some stuff for pre-processing, including images, I think, but yeah, it comes with lots of stuff. It's built also on NumPy. It also has like plotting stuff inside, so you can actually plot the outputs. It comes with Anaconda, which is already installed on your laptops, but yeah, you can also install it on your own computers like that if you ever need it. That's a quick overview, like a cheat sheet of stuff which is pre-implemented. So yeah, classification. There's different algorithms for each. So even if you have like a classification problem you want to tackle in your research, you can play around with like SVC, different nearest neighbors algorithms, etc., etc. So the thing also with sklearn is usually the API of all these different implementations are very similar. So let's say you have like a function, predict X, and the output is Y, to predict some results out of your model. The syntax, like the name of the function and the parameters of the function, it's the same for all of these. So basically you can plug and play, you can switch around different algorithms, you can switch around different models, etc. And it kind of works. You can force any model on your data, and all of them have more or less the same input, like the same way to address them. So it's very nice for quick prototyping and playing around with different algorithms. The first one we want to talk about is like the iris dataset, which is basically a dataset based on flowers. So there's like these kind of different flowers, and the dataset basically has like different values, like the length of the petals and the sepal, well, different kinds of like characteristics for each flower. So that's like a biology dataset, I think, where basically you have like lots of different values for different species of flowers, and like which characteristics does each of these flowers have based on samples. So your standard dataset based approach. So we have this dataset, and now let's put a model on it to see whether it generalizes in any direction and whether we can like predict the species for other input data. So there's this file, iris_datacheck, which should be part of your download thing, I think. So you could run it probably, hopefully. So what it does basically, I also have it over here. I can just open it. That's the white one, data check. Data check. Next one, data check, visualization. Okay. So first data check. So basically we have this one. We use sklearn. Sklearn actually has this kind of submodule which is called datasets. So it has some kind of datasets, let's say, pre-installed. So if you want to play around with sklearn and you don't have a dataset, it gives you a couple of datasets just to try the algorithms. So the iris one is actually part of that, I think. Yeah. So pandas, it's a different library, which is, yeah, it's a library for data processing. It's very handy when you load data and stuff like that, or pre-process data maybe, text-based data. So yeah, the script proceeds. We load the dataset in a variable which is called iris, and then we create a data frame out of the data with columns which are the feature names. So basically we just had this table with like the different like petal width, petal length, stuff like that. That would be like the different feature names, and this function would just create like a neat data representation of that in the memory. So first it would like print out the data, and then yeah, I think that's all the script does first. So let's try to run it, and hopefully it runs, because I haven't tried it. It should run on your computers, I think. Okay. So basically, if you're in the right directory, you can go into the directory with like the cd command David explained yesterday. And then you can run like Python space and ed's data check. And that one should actually like load the dataset into the memory. It outputs some kind of warnings which we can just ignore. It's basically, yeah, some kind of because the script is old. So this one just gave us the data. So like if we go up here, it's basically, for example, the data set is like, okay, for every sample, 0, 1, 2. Again, notice it's 0 index, so the first element is 0. So for every element, we have like different values. So this element, this length is like 5.1 centimeters, and etc., etc. And the petal width is 0.2 centimeters. So we have like the data set loaded into the memory. And so yeah, this script first just puts out all the different like what's inside the data set. So the data set has 150 rows, which basically means 150 different samples, and 5 columns. So for every sample, we have 5 different values. So next, we look into the visualization. That's our second script. And why doesn't it load? Okay, it loads. So again, in this script, by the way, other than MATLAB yesterday, where we had like this tool in which we were working, and we had like kind of a workspace, and we just loaded in scripts, and it was saved into the workspace. Python is just single scripts we run. So if we run one script somewhere and then the second script somewhere, we can't really share data. So in our second script, we need to load the dataset again. The first one was just to show the dataset. Now we actually want to do something with the dataset. So this one is called iris visualization. So we try to visualize this. We try to visualize the data. So first, we just load the dataset again. It's pretty much the same as in this other script. We load the iris dataset, the features, so that's basically the data itself. The feature names is like the name of every column, which is kind of like, you don't really need it for machine learning purposes, but obviously you want to know what the result means, or etc. So if you plot it or if you visualize it, you can also plot the feature names. And the targets would be like the actual results. So like for every sample we have like the size of the petals, etc. And the target would be what flower is it actually, like which species is it. So that would be like the, if we do machine learning, we train a model on all the data, like the size of the flowers, etc. And the result obviously is the species, because we want to predict what species is each flower, or what species is each data sample. So that's the target. So in other words, that's X and that's Y in math. But first we do a small visualization. So basically like this. I always skip the details, but basically we create a figure, which is like a nice way to say we create a plot. And then we, like a for way is what we looked in earlier, like going over every element of something. So we go over like combinations of the data, and we create a scatter plot based on that. And then the labels are like our feature names, and then we put it in a nice grid. So, and in the end, the result is shown. So basically, this script loads the data, and we will plot it to look at how it will, like how does the data look like. We don't do any machine learning, but we just plot and see what data do we actually have. So again, we will run this one. Hopefully it works. Where does it actually open it? I'm not sure. Does it open a new window? Still calculating. I mean, while it's calculating, I can just also show you the results inside the slides. So basically, after it's done calculating, this is the result. So basically, the just, how many lines did we have? Like 20 lines, 15 lines? Maybe not even that. We had a little bit more. We had like 30 lines. So having 30 lines like this, that's basically the output. It just finished calculating. So our code produced this. So that's the result. If you run the script on your computers, basically this window should come up if it works. We just plotted like the different columns in the data set into graphs. So this is where we can already look at the data. The 3 different colors are the 3 different species. So we have 150 samples. I'm not sure, maybe 50 of each. I'm not sure. But basically, like this, you can already see as a human, you can see, like, for example, like the red one, it has very different characteristics. It's kind of far away from the other samples, like on these 2 ones and also down here. The other ones are a bit more clustered, but even here you can kind of see. You can probably find like a graph which goes through and like separates these. So that's what machine learning does. It uses the data, and you create some function to separate the data. Lastly, let's use the same data set to actually do some machine learning. So that's in this file, which is called iris classification all features. So again, in the beginning, we import all kinds of stuff we need. This time much more. So again, there's some kind of data set we want to load, namely the iris data set we just talked about. And then there's different machine learning approaches we want to include. So here, first is like inside the package model selection, there's some kind of training test split function where you can like do this 80-20 split of your data. And then we want to train a linear SVC. So for classification, obviously nowadays most people do machine learning, but all these standard algorithms would be random forest, support vector machine, etc. That actually is like a linear support vector classification. So it's a support vector machine. And then we also have some metric results. So basically we can like output like a accuracy or like a confusion matrix out of the data. So again, we load the data set. The features is basically all the data, which is like the x values. So inside your data, like the x values you want to train your model on. The target is the y values, like what's the species of every sample. And then you do like a training test split. So usually in machine learning, you want to use, like, let's say 80% of the samples to train your model, and 20% of the samples to then test your model if it works. Like, can it predict the species correctly in this case? So that's what it does. So basically, you put in like your x and y values, and 20% would be the test size, so 80% is the training size. It creates like two data sets. And then we have our classifier. We can fit the data using the training data and the labels for the training. So that again would be the x values and the y values. Fitting. And that's all. Basically, this function already does like the main machine learning, like that does the training part of the machine learning, where you basically train a model and you just put in x and y. And one of the good things of Python and also of sklearn is basically that you see it's very easy. Like, you have a classifier fit x, y. And it works for anything like that. So whether you have SVM, whether you have your random forest or any other algorithm, that's your syntax. So you can very quickly actually switch between different syntaxes, between different algorithms. And then this basically, until here, we do training. So at that point, the model is trained. And then the result, this is just predict. So basically here, you can just put in any new data, and it will predict the species. And lastly, there's a couple of helper functions from sklearn which can just put like stuff like a confusion matrix, classification report, and accuracy score. It's actually functions from sklearn which can just output these result matrices conveniently with one function. So again, if you go to the terminal, if you're in the right directory, you can like go to like Python, iris, what was the name? Classification, something? Yeah. So this function, I put it twice. So Python space iris classification all features. Basically, now it will first load the dataset. Maybe it takes a couple of seconds, so I will go back to the code. It first loads the dataset, x and y. It splits the data 80-20. It trains the classifier, which is a linear SVC, so a support vector machine. And it trains the model. It predicts some results based on the test dataset, and then it will print out like confusion matrix, etc., etc. So it finished calculating. So basically, that's the result of our trained model. The confusion matrix looks like this, the F-score is like this, and the accuracy is 100%. So it just calculated everything correctly, which is probably because the dataset is very easy. So again, if you look at the samples, obviously the red one you will never misclassify because it's so far away from all the other samples that you will always get it correctly. The green ones and the blue ones, they might be a bit more tricky, but even then, if you combine multiple features, it's enough information that you can always classify it correctly. So using these, I don't know, like maybe 50 lines of code, you can kind of load all your data. You can train a model, in this case an SVM, and then do like a report of the actual model, like report like the accuracy and the confusion matrix, etc. So that's the result. Basically, the confusion matrix would be something like this. So you can see like the middle one would be the correctly classified results, where like we have 3 different classes, which are the 3 different species. And in this one would be where the ground truth is equal to the predicted value, which basically means it's correctly predicted. And if you look at the confusion matrix, it predicts everything except one sample, which was misclassified for some reason. So the accuracy would be like 97% in this case. On my terminal, actually, it was 100% for some reason. Yeah, actually, in my terminal, it classified everything correctly for some reason. So there, it worked even better. But yeah, the mileage might vary. Anyway, that's one way to classify to classify data based on your data set and a model. sklearn also comes with lots of different other stuff. So as I said before, there's like naive Bayes, different nearest neighbor approaches, there's like ensemble algorithms, even neural network, even though you might say if you use something like deep learning, sklearn is probably not the best choice. There's other libraries for that, like Keras and PyTorch, etc. But it's available. So I think we don't have code for that. That's just a couple of different examples. So basically, that one uses an SVM based on one feature. So here we just plotted out like the petal length and the petal width. So if you have just these two features, you can already pretty easily distinguish between two different species. Where's the feature? I think there might be actually the code for that somewhere. Just a moment. Visualization data check, warm up. That's just a thing in the beginning. Yeah, I don't think we have the code for that actually as code, but so essentially, yeah, it pretty much does the same as before. Like we load our data set, we divide our data set in like training and test data. In this case, actually, we don't even use a function, but we just define it ourselves. And then basically we just have this one line, the fit, training data, training labels, which is x, y, and train our model. And then we plot it. That's basically all of our slides. I quickly want to show another example. When's the end? 30? So we have about 15 minutes left. There's another noteworthy thing which is called matplotlib, which is probably what you want to use at some point if you use Python. So matplotlib is already used by sklearn and I think also NumPy. It's basically a plotting library, what the name suggests. So that one, you can create nice graphs like these with Python. So obviously you are in data science or engineering, so you probably want to plot your results. It can go from simple line plots to more advanced images where you kind of like plot different points if you're in some kind of medical background. You can also do like contouring, histograms, etc., etc. or draw a nice heart, I guess. 3D plotting. There is, if you are into stuff like 3D plotting or even interactive stuff, there's also another library called Plotly-lib, something like that, where you can even have like interactive stuff. I mean, we have a bit of time left, so I can just show that maybe afterwards. But stuff like streamplots, different stuff like that. The matplotlib is always a bit tricky to use. But on here, basically everything comes with example code. So you can basically download the example code and work from there. So if you need like a stacked bar graph like this, the code is still kind of easy to look over. So you can, it's just like, again, it just prepares the data. So you have like your what is it actually about? Some kind of like men and women, some scoring between men and women. So we have like the result, like the data set itself, and then you can create like a bar for the men and a bar for the woman, and then just set like the different like the ticks, like what kind of intervals do you want to have, or what kind of title you want to have, and then you can plot it. You can also just, I mean, I think the show function, as we saw before, it will just put it on the screen. There's also like you output as a PNG or JPEG or something. So you can create your results like that. There's also a very nice tool called Plotly, I think. Here's that one. Which goes a step further. I think, I'm not 100% sure, maybe it's built on Matplotlib in parts. But what it essentially does is having like a interactive interface to plotting. So it usually takes forever to load because everything is rendered inside the browser. But if it loads at some point, you can basically just like move around stuff. Like you can have interactive stuff like inside MATLAB. MATLAB probably has it. Are there some kind of examples? Quick. Not over here. It does. Dash Plotly examples. So quick gallery. Yeah, it usually loads forever, but when it loads, basically you can use it to create something like demos based on your data. So like this, which is like now I think here it's just a video, but basically you can kind of like interactively play around with your data. You can move around, you can switch samples on and off, stuff like that. And you can just create a small app like that out of Python, which is kind of handy if you want to create a demo based on your work or just for your own visualization for your research, I think. So stuff like that is very handy. I use it in my own research actually quite a bit. Also like, yeah, stuff like this, you can create dashboards and stuff. Yeah, for research purposes it's also nice. So we have kind of 10 minutes-ish left, but I'm kind of done with my part for now, I think. So does anybody have any questions based on Python or libraries or anything else? You can obviously, if you're interested in the examples, look at them later or play around with them. I think it's a good introduction also to machine learning in general if you have never used machine learning.